Hey everybody, Mr. Hayes, Mr. Hayes' World of Math. We're talking about inference. This is going to be formalizing the concepts that we were talking about in the caffeine experiment, where we were trying to see if what we were seeing actually made sense for, if what we were seeing made sense, if it was actually the caffeine or something else. And so we compared it to random chance, and we discovered, hey, we've got a large chance that this is not actually happening due to the caffeine. So the important ideas are this. The first one we have is sampling variability. There are a couple different ways that the number of the size of the sample is going to determine how what the variability of it is. Okay, so for example, different samples yield different estimates. If you think about it, that makes sense because each of the samples don't have the same individuals in it. So that means your averages, your means are going to be different. So you got to be careful of that. Larger samples produce more accurate estimates. And we're going to talk about it. Basically, if you think about it, if you have an outlier and you only have 5 items, then that difference of that outlier is only spread among the other 4. And so that's going to shake your average. If I had 100 of them and that was my only outlier, that's going to be shared among 100 different ones. It's the same kind of reason why if you take your first test and you take your second test, you can really swing your grade a lot because you only have 2 tests in that test category. By the time you get to the end of the semester and you're taking your 5th or 6th test, you can't swing your grade that much because that test, even if you ace it, has to spread that out all among all the other tests to kind of help fill in the gaps. And lastly, there's something called margin of error. And you may have done this in science class already. Margin of error creates an interval of plausibility where you're able to kind of say, all right, this is what we saw. The true one is probably in between here and here. And we'll talk more about that later in coming chapters. But basically, you're going to have a sample estimate, and you're going to add and subtract the margin of error. That doesn't look, make that a little bit bigger. So you're going to add and subtract that margin of error. So you can say, all right, we can go up, let's say 5%. So if I have an 18% thing, that means that it's going to be up to 23 and down to 13. President elections, surveys, you always say it has a margin of error of 3.2%. That's what we're talking about. Now, in terms of statistically significant, this is one of the other big ideas to come out of this chapter that you need to kind of have in the back of your head. So when the results from a study are too unusual to have happened purely by chance. So what you're seeing, something had to influence it. We couldn't just randomly do it and have it work out. And we're going to talk more about that stuff again as we go through probability and then on the other side of probability. But so you've got some sort of simulation here. You can see the dot plot. This line here is going to be what your sample was. And so what we're trying to do is saying, okay, what percentage of that values are at that sample size or bigger? And that's going to be the percentage of the times that we could expect to see what we were seeing. So the proportion of dots, if it's less than or equal to 5%, we're going to call that statistically significant. Okay, so less than 5%, we're going to say, all right, you know what? Or less than or equal to. We need to look at this closer. There's something probably going on. If it's bigger than 5%, random, it could have just happened by chance. So for the check your understanding, you're going to go through and we're going to talk a little bit about pulling samples out of the National Football League, specifically players, and you're going to average 50 of them. And you're going to say, okay, that sample has an average weight of 244.4 pounds. So hit pause, answer the questions. See you in a minute. All right, so first one, do you think that 244.4 pounds is the true average of weight of the NFL players? It's really only a sample, right? Do you think you hit the true one right out? Remember, the true mean can only come from if you have the whole population. So here, all samples are going to be different, so we can't guarantee that it's going to be the actual true mean. The only way to have it is if you average the whole entire population. So we don't expect our sample mean to actually be equal to the true mean. It's going to be an estimate of the true mean, but it's not going to be the true mean itself. Okay? If another random sample of 50 players is taken, would you expect that average weight to be exactly 2,000 pounds? They're big, but not that big. 244.4 pounds. And again, like we set up above, all the samples are different. You have a different group of 50 players. Even if you had 49 players the same, you're still going to have a 50th player in there, and it's going to make the weight different. Are there going to be times you might get a sample of 244.4 pounds? Sure. Are you always going to get that? No. All the samples are going to be each individual samples. And lastly, what's going to be more likely to have an estimate of the true weight of all NFL players? A random sample of 50 players or a random sample of 100? Now, like I said above, the more people you have in a sample or more items you have in a sample, the more numbers you have a chance to spread out that difference of an outlier. So in this case here, the random sample of 100 is going to be larger. And we're going to spend time talking through that in some of the experiments and experiences we're going to be having in the future. So one more section out of 4.3. I'll see you tomorrow. If you have any questions, feel free to either send me an email, drop me a comment down below. We'll see you in a bit.